Hello everyone, this is the video summary for the ESTCP project ER185168. Our project is to demonstrate the use of in situ co-metabolic biodegradation as a cost-effective tool to treat 1,4-dioxane and common chlorinated co-contaminants in deep, large dilute plumes. I am the principal investigator, Jacob Chu. Dr. Michael Hyman is the co-principal investigator. Remediation of deep large dilute plumes is a main challenge at some Department of Defense or DoD contaminated sites. In a statement of need issued in 2007, the DoD was seeking for a more cost-effective solution to remediate large dilute plumes with a focus on deep plumes. The words large, dilute, and deep plumes are highlighted in 3 red ovals on the slide. Such plumes at the DoD sites often contain contaminants like chlorinated volatile organic compounds and 1,4-dioxane. There are several DoD sites that have deep large dilute plume challenges that require a large financial commitment for cleanup. For the following slides, I will use the acronyms CVOCs to refer to chlorinated volatile organic compounds and 1,4-D for 1,4-dioxane. Now let's briefly talk about typical hydrogeology settings for sites where a deep large dilute plume is formed. The scale of such a site is generally many acres. There may be a single large source zone or multiple separated sources. The source locations are often situated in either natural or artificial topographically low areas. On the left side of the slide, a conceptual site has 3 sources in topographically low areas. In these areas, natural focused recharge helps push contaminants in the vadal zone into groundwater. The vadal zone for a deep plume is thick. The depth to groundwater is often more than 100 feet deep. The complexity of embedded low hydraulic conductivity lenses in the vadal zone can result in a tortuous contaminant migration pathway, making it difficult to fully characterize the contaminant mass distribution in the vadal zone. In fact, it is often technically impractical to remove the contaminant mass in the deep vadal zone. Therefore, the residual contaminant mass in the deep vadal zone becomes a long-term source to sustain the growth of a deep, large dilute plume. The total contaminant concentration in a large portion of the deep large dilute plume is often lower than 100 micrograms per liter. The conventional way to remediate a deep large dilute plume is the pump and treat approach, as shown on the left side of the slide. Pump and treat is a proven technology for plume containment or plume interception. When 1,4-dioxane is among the contaminant suite, an advanced oxidation process, or AOP, is needed to treat 1,4-dioxane ex situ. AOP is an energy-intensive treatment process and may require a large amount of reagents. AOP is associated with a high system operation and maintenance cost. If there is no 1,4-dioxane in the plume, pumped groundwater may be treated with the considerably more cost-effective granular active carbon, or GAC. The presence of 1,4-dioxane is frequently the driver to use the AOP. To improve the cost effectiveness of treating a deep large dilute plume that contains 1,4-dioxane, this ESTCP project was set to demonstrate that an in situ high-rate bioreactor can be a cost-effective alternative to treat 1,4-dioxane and some co-contaminants. On the right side of the slide, it describes the approach of using the combination of in situ high-rate bioreactor and the GAC to treat a wide spectrum of contaminants. First, the core biological process for the in situ bioreactor is aerobic co-metabolic biodegradation, which can degrade 1,4-dioxane and several CVOCs. The use of a GAC unit can help remove some more recalcitrant CVOCs, such as 11-DCE, 111-TCA, and PCE, that cannot be readily degraded by aerobic cometabolic biodegradation. In addition, the use of a GAC unit can also reduce CVOC concentrations that may interfere with the performance of the in situ high-rate bioreactor. The overall objective of this demonstration project is to show that in situ aerobic cometabolic biodegradation can be a cost-effective approach to treat deep, large dilute pollution of 1,4-dioxane and the coronates VOCs. The cost-effectiveness of the tested technology is to be judged against the conventional pump and treat technology that uses an advanced oxidation process. A conceptual diagram of the combined GAC and in situ high-rate bioreactor technology is shown on this slide. On the left side, you can see that the technology uses an angle well to extract impacted groundwater. Substrate addition to pumped groundwater was done in an underground vault. Then pumped groundwater is injected through the other angled well. The substrate loaded injectate helps establish an in situ bioreactor to degrade contaminants, primarily 1,4-dioxane. The use of angled wells is ideal for the deep pollutant treatment because it can eliminate the long pipeline needed to connect a traditional injection-extraction vertical well pair. Therefore, the use of angled wells also helps circumvent potential site access constraints that may limit the use of groundwater recirculation-based treatment technologies. A closer look to the substrate addition system is shown on the right side of the slide. Extracted groundwater may pass a GAC unit when there is a need to remove some CVOCs that cannot be readily treated by the in situ bioreactor. Nutrients that can promote microbial growth of aerobic cometabolic biodegradation bacteria can be metered into recirculated groundwater. To control potential bioclogging that may occur in the vicinity of the injection well, inhibitors like hydrogen peroxide or acetylene may be also added on a needed basis. A hydrocarbon gas, typically propane or hydrocarbon gas blend, can be used as primary substrate or food source to grow and maintain aerobic cometabolic biodegradation activity. Oxygen is also needed to sustain the respiration of aerobic cometabolic biodegradation bacteria in situ. To enhance gas addition into recirculated groundwater, gaseous substrates are metered using a gas mass flow controller. Gaseous substrates are solubilized into recirculated groundwater using a Venturi injector. Let's switch the gear a bit to talk about aerobic cometabolic biodegradation. Conventional biological wastewater treatment and bioremediation use the microbial metabolic capability to degrade contaminants. For metabolic contaminant biodegradation, the target contaminant is used as a carbon and energy source. A decrease in contaminant concentration can be expected to involve an increase in the size of the contaminant-degrading microbial population. Using hydrocarbons as examples, as shown in the upper part of the diagram on this slide, hydrocarbons such as methane, propane, and toluene may be used by certain types of aerobic hydrocarbon-degrading bacteria as growth substrate or food source. These bacteria can express enzymes like oxygenase or monooxygenase to metabolically degrade hydrocarbon substrates and use oxygen for respiration. The harvested energy and carbon molecules through degradation can be used to support microbial growth. Now let's look at the lower part of the diagram. Many emerging contaminants such as 1,4-dioxane, 1,2,3-TCP, and NDMA have been shown to be degraded by malloxygenase fortuitously. However, environmental relevant concentration of these contaminants are often too low to support the growth of the microbial population that degrade these contaminants, and thus exogenous primary substrates are needed to sustain the microbial population. In this case, because contaminants biodegradation is fortuitous and has no metabolic benefits, we call the contaminant degradation process is cometabolic biodegradation. For our ESTCP project, we selected the Air Force Plane 44 site in Tucson, Arizona for technology demonstration. The primary contaminants in impacted groundwater are TCU, ONDC, and 1,4-dioxane. The deep, large plume at the site is managed using a pump and treat system and an injection well gallery that returns treated groundwater back to the aquifer. The shapes of the TCE and the 1,4-dioxane plumes are shown in the two figure panels at the bottom of the slide. The high concentration source zone for TCE and 1,4-dioxane are on the right side of each figure panel, which is also shown as a darker colored area. The extraction well E18, which is in the central part of each figure panel, was the primary pumping well to capture impacted groundwater from the source zone. The pumping well E01 on the left side of each figure panel, which is located down gradient of E18, was capturing the more diffusive portion of the plume. The approximate field test area for this demonstration project is shown as a red box near E01. The top of the aquifer near E01 is about 100 and 120 feet below ground surface. Based on the boring logs near the field test area, as shown on the right-hand side of the slide, it appears that the depth interval of the plume is between approximately 120 feet and 140 feet below ground surface, which also coincides with the coarser grain portion of the aquifer. Although we expected to see dilute concentration of 1,1-DC TCE 1,4-dioxane in our field test area, the pump and treat operation at the site was terminated to allow upgrade of the on-site treatment system during the laboratory treatability study of our demonstration project. Because of no groundwater extraction to contain the source zone groundwater, a high concentration plume core migrated from the source zone to our field test area. The table in the middle of the slide shows that the 2019 total contaminant concentrations at the nearby well E01 was lower than 50 microgram per liter. During the treatment system shutdown in 2022, the contaminant concentrations at E01 increased substantially. Although the pump and treat system started again at the end of August 2023, the TC and the 1,4-dioxane concentrations remained noticeably higher than the 2019 levels. The configuration of the remedial system of our demonstration project was shown in this slide. The left-hand side is the plane view of the well network, and the right-hand side is the vertical cross-section view. From the vertical cross-section view, you can see that the angle wells were drilled at an angle approximately 17 degrees, deviated from the vertical direction. The separation distance of the well bottoms of the angled well pair are about 100 feet. The extraction and injection wells were connected inside an underground vault approximately 12 feet long, 4 feet wide, and 2.5 feet deep. The 3 monitoring locations were selected inside the recirculation zone between the angle wear pairs. Notably, the MA1 is the nested well system consisting with an upper screen interval and a lower screen interval. From the plan view, you can see vault and the well locations, as well as the cage area for hydrocarbon gas tanks and the cage area for oxygen gas cylinders. The well bottom of EXA is about 25 feet away from the on-site pumping well E01. For the next few slides, I will walk through several project phases according to the chronological order. After site selection, the laboratory treatability study was conducted. The major findings of this laboratory study were: number 1, no aerobic cometabolic activity detected in the native microbial population. Number 2, several aerobic cometabolic microbial strains can grow inside groundwater under the dilute pollutant concentration, with additional nitrogen and phosphorus nutrients. These added microbial strains show faster growth. Number 3, Mycobacterium vaccae JOB5 strain was selected for bioaugmentation. Because of the termination of the on-site pump and treat operation, when we characterize the baseline condition, high TCE, 1,1-DCE, and 1,4-dioxane concentration were found in the field test area. These concentrations were found comparable to the concentration levels found at some source zone monitoring wells. We later found that the JOB5 strain could not grow in such groundwater conditions, primarily due to the toxicity induced by 1,1-DCE cometabolic biodegradation. An oxygen tracer study was then conducted to assess the travel times from the injection wells to various monitoring wells in the recirculation zone. It takes half day to reach both the upper screen and the lower screen intervals at the MA1 location. It takes 2.6 days to the MA3 location. The tracer study results also revealed that the lower portion of the aquifer unit is significantly more permeable than the upper portion. This conclusion was based on 2 facts. The first fact is that a faster oxygen signal breakthrough at MA2 were found when the oxygen probe was placed closer to the well bottom. The second fact is that the oxygen signal breakthrough at the MA1 location occurred almost at the same time, indicating a faster signal transfer in the lower portion of the aquifer, because the separation distance between the injection well and the lower screen interval of MA1 is larger than the separation distance between the injection well and the upper screen interval of MA1. This slide will show the results of the biostimulation phase. This phase occurred between June and September 2023. During this phase, propane and oxygen were added continuously into recirculated groundwater. Oxygen level remained high. Propane concentration gradually increased from 0.5 mg per liter to about 2 to 5 mg per liter. The concentration trend during this period are shown on the graph on the right-hand side. The x-axis is the date in 2023, and the y-axis is for concentration. There is no sign of propane concentration decrease, signifying no aerobic cometabolic biodegradation activity. This is consistent with the observation that no removal of 1,4-dioxane and the TCE in situ. As the 1,4-dioxane and TCE concentrations during the biostimulation phase are similar to the concentrations observed during the recirculation baseline period. In order to enable successful technology demonstration, we would like to establish an in-situ bioreactor that can treat a high recirculation flow rate, which can cover the groundwater flow over a prune width of approximately 100 feet. We used a mobile GAC system to remove toxic 11-DCE, which helped establish the bioaugmentation culture in situ for 1,4-dioxane biodegradation. During the bioaugmentation phase, the target's recirculation rate was 13 GPM. The results of the bioaugmentation phase shows that the GAC system effectively removed 11-DCE and TCE. We also achieved a strong in-situ 1,4-dioxane biodegradation by injecting recirculated groundwater that is free of 11-DCE and TCE into the recirculation zone. We also observed strong metric diffusion effects in the groundwater recirculation zone, which complicated performance monitoring. More detailed 1,4-dioxane biodegradation performance data is shown on this slide. There is lots of information on this figure. First, the x-axis describes the days since the start of the bioaugmentation phase. The bioaugmentation phase is the time between day 0 and day 280. The negative sign before the day means it is before the start of the bioaugmentation phase. The biostimulation phase is around negative day 260 and the negative day 180. As shown in the yellow highlighted area, the baseline recirculation phase is shown around negative day 330 as a light blue highlighted area. The y-axis shows the 1,4-dioxane concentrations. The red triangle symbols show 1,4-dioxane concentrations over time at the injection well INJA, and the green circle symbols show 1,4-dioxane concentrations observed in the bioactive zone in situ. When you see the top portion of the bioaugmentation phase, you can see the text indicates the GAC operation started on day 0. You can also see a text box below shows the period of 1,4-dioxane breakthrough of the GAC unit. It takes approximately 75 days for a completed 1,4-dioxane breakthrough of the GAC unit. The group of the text boxes below that indicates that the bioaugmentation phase is divided into 3 distinct periods. The first period is the JOB5 culture period. At the beginning of this period, the JOB5 culture was added to the recirculation zone. During this period, a low propane mass loading rate was used, which means that the propane concentration injected ranged from approximately 100 and 500 microgram per liter. This period lasts about 100 days. The unstable system operation period then followed. During this period, the recirculation operation was intermittent due to some malfunction events of the groundwater pump and the oxygen injection apparatus. This period lasted approximately 60 days. Right after this unstable operation period, the other bioaugmentation event occurred. We used one pure culture called Rhodococcus rhodochorus strain ATCC2119A and 2 mixed cultures called Nova 5 and Comet 1 respectively. These cultures were shown to degrade 1,4-dioxane and/or TCE in a laboratory setting. Therefore, this period is called the NOAA 5 plus 2119A plus Comet 1 period. During this period, a higher propane mass loading rate was applied to the recirculation zone. The figure shows that before the start of the bioaugmentation phase, the 1,4-dioxane concentrations at the injection well under the baseline recirculation phase and the biostimulation phase are around 70 microgram per liter. The JOB5 culture was used for bioaugmentation. After the start of the bioaugmentation phase, the initial 1,4-dioxane concentration is very low due to temporary 1,4-dioxane removal by the GAC unit. After about 2 months operation, 1,4-dioxane returned to the previous high level as a result of a complete 1,4-dioxane breakthrough. During day 0 and day 100, we introduced propane at a lower mass addition rate into recirculated groundwater. A small separation between the injection well concentration data in red symbols and the concentration in a in situ bioactive zone, which are in green symbols. The gap of these two data trends indicates that the in situ biotreatment zone did not effectively decrease the 1,4-dioxane concentration under the low propane mass addition rate. For the monitoring well MA3 and the upper screen well at the MA1 location, the concentrations observed at these two wells were likely affected by the effects of matrix diffusion. We will discuss the matrix diffusion effects observed at these two wells in a later slide. Between day 100 and day 150, the system operation was unstable and resulted in intermittent groundwater recirculation operation. Interestingly, larger concentration differences were observed between the injection well red symbols and the bioactive zone concentration during this unstable operation period. It is likely that the intermittent recirculation operation led to a longer residence time of injected groundwater stay inside the bioactive zone, thereby allowing more 1,4-dioxane biodegradation. So, to enhance the 1,4-dioxane biodegradation rate, a higher propane loading rate was used to support a larger population of bacteria that could carry out aerobic cometabolic biodegradation. Propane concentrations injected during this high propane mass addition period were increased to 2 to 5 milligram per liter. The propane injection durations and frequencies were also gradually adjusted from shorter and more frequent pulses to longer and less frequent pulses. In the beginning of the higher propane mass addition period, additional microbial culture were also introduced, as we just previously mentioned. After approximately 50 days of this high propane mass addition period, the 1,4-dioxane concentrations dropped to an average level approximately 2 micrograms per liter, showing a consistent performance in the later part of the high propane mass addition period. To assess how the bioactive zone could be affected by starvation, no propane was injected for a brief period of a week, which is shown as a red box near day 224. The brief starvation period appears to result in an increased 1,4-dioxane concentration observed in the bioactive zone, indicating the performance of a bioreactor is sensitive to the primary substrate loading rate. Based on the average concentration of injectate and the average concentration measured in the bioactive zone, the single-pass treatment efficiency was estimated to be 91%. This treatment efficiency is associated with the degree of treatment when impacted groundwater passes the bioactive zone only one time. Because a portion of treated groundwater was passed the bioactive zone more than one time due to groundwater recirculation, the overall treatment efficiency was estimated to be approximately 97% based on the average 1,4-dioxane concentration in recirculated groundwater when no aerobic cometabolic biodegradation occurred. In this slide, we will show the evidence of matrix diffusion in the recirculation zone, which interfered with performance monitoring. During the bioaugmentation phase, the GAC unit was used to remove TC and 11DC from recirculated groundwater. As shown on the figure, during the baseline recirculation phase and the biostimulation phase, the injectate had a TCE concentration approximately 300 micrograms per liter, and this concentration also throughout the recirculation zone. After the use of a GAC unit, the injectate had a TCE concentration less than 1 microgram per liter most of the time, as shown in the red triangle data on the right-hand side of figure. However, TCE concentrations observed at MA3 and at the upper interval of MA1 were generally above 10 micrograms per liter and could reach near 100 micrograms per liter. It was found that during the period of intermittent recirculation due to unstable system operation, the TCE concentration at MA3 spiked much higher, which likely resulted from a greater magnitude of TCE matrix diffusion during the period of slower groundwater movement in the recirculation zone. One common system maintenance issue for the recirculation-based in situ bioaugmentation is that frequent bioclogging may occur at the injection well that receives groundwater loaded with microbial growth substrates. One of the project goals is to optimize the primary substrate loading rate for treatment performance, but at the same time keep the magnitude of bioclogging in control such that there is no need for injection well redevelopment. The observed water level data at the injection well shows that the magnitude of bioclogging increased during the high propane mass addition period, which was between approximately day 150 to day 275. There was a one-time spike of water level above the performance threshold water level, which is 40 feet below top of the well casing. It was hypothesized that this water level spike might be related for an experimental period, which constant 1 propanol injection for a 4-day period was used to boost the aerobic cometabolic biodegradation activity. After the observation of this water level spike, the injection of 1 propanol stopped, and a gradual decline of water level in the injection well followed. The result indicated that a higher degree of bioclogging induced by 1 propanol injection appeared to be reversible, and the degree of bioclogging can be controlled by optimizing the primary substrate loading rate. In this slide, we will briefly talk about the microbial data collected during the demonstration test. We monitored the abundance of various functional genes associated with various types of monooxygenases. The names of these monooxygenases are shown in the yellow highlighted text on the slide. They are propane monooxygenase, or PPO, phenyl hydroxylase, or PHE, toluene 2 monooxygenase, or RDEG, toluene 3 and 4 monooxygenase, or IMO, and the short-chain arcane monooxygenase, SCAM, or SCAM. The results of the relative abundance of these monooxygenases are shown on the upper right corner. During the baseline and the biostimulation phases, SCAM, which is in green color, was detected, but the relative abundance is no more than 20%. On the right-hand side of the graph, you can see that the 3 bioaugmentation cultures used on day 141 contained PPO, SCAM, RDEG, and PHE. However, toward the later time of the bioaugmentation phase, which are the data collected on day 237 after the start of the bioaugmentation phase, scan become dominant, it appears that the bacteria expressing other types of monooxygenase did not thrive in the in situ bioactive zone during the bioaugmentation phase. We also characterize the microbial population composition to the genus level. The results are shown in the lower left corner. During the baseline and the biostimulation phase, Mycobacterium, which is in green color, was detected, but the relative abundance is no more than 1%. However, toward the later time of the bioaugmentation phase, which are the data collected on day 237, the Mycobacterium population were enriched. This is a big difference in comparison with the microbial population compositions observed in 3 bioaugmentation cultures, which is on day 141. The results show that Mycobacterium outcompete other genera such as Rhodococcus and Pseudomonas in the bioaugmentation phase. The genera of Rhodococcus and Pseudomonas also contained various types of bacteria that can express monooxygenase and utilize propane. However, these two genera did not thrive in the recirculation zone during the bioaugmentation phase. To evaluate the cost competitiveness of the combined GAC and in situ aerobic cometabolic biodegradation technology, we compare this technology with the conventional pump and treat technology that utilized an advanced oxidation process called hypox for CVOCs and 1,4-dioxane destruction. A few key assumptions for this comparative cost evaluation are described using the bullet points on the left side of the slide. The pollution is assumed to be 130 feet deep below ground surface. The pollution width is 360 feet. The aquifer has a hydraulic conductivity value of 100 feet per day. The impacted groundwater contains PCE, TCE, 11-DCE, and 1,4-dioxane. For both technologies, reinjection of treated or to be treated groundwater is allowed. Finally, for both technologies, treatment can attain all cleanup goals. On upper right corner of the slide, the groundwater flow field simulation shows that to intercept the plume, 3 recirculation well pairs are needed for the combined GAC and in situ aerobic cometabolic biodegradation technology. The total recirculation flow rate is 60 GPM. On lower right corner of the slide, the groundwater flow field simulation shows that to intercept the plume, 2 pumping wells are needed for the pump and treat technology. The total pumping rate is 45 GPM. It is noted that a higher total flow rate, 60 GPM, is needed for the combined GAC and in situ aerobic cometabolic biodegradation technology. This is because a portion of the flow rate is used to establish groundwater recirculation for the combined GAC and in situ treatment technology. Using our cost data obtained from this ESTCP project and our other project experience in using hypox for advanced oxidation treatment, the cost evaluation results are summarized in the table on the slide. The combined GAC and in situ aerobic cometabolic biodegradation technology is more cost-effective in terms of both the capital cost and the 30-year operation maintenance monitoring cost. The 30-year overall total remedy cost of the GAC plus in situ aerobic cometabolic biodegradation technology is only 57% of the cost of the pump and treat technology. Energy and chemical costs are the main factors resulted in a higher operation and maintenance cost for the pump and treat technology. When the electricity cost is estimated based on 28 cents per kilowatt hour, the 30-year total remedy cost for the GAC and the in situ aerobic metabolic biodegradation technology can cost less than half of the cost for the pump and treat technology. In the beginning of this project, we set 4 primary performance objectives. These objectives are in the first column of the table shown on the slide, which are remediation effectiveness, cost effectiveness, bioclogging, and the benefit of angled wells. For remediation effectiveness, the combined GAC and in situ aerobic metabolic biodegradation bioreactor is able to achieve concurrent treatment of 1,1 DCE, TCE, and 1,4-dioxane. The GAC unit can readily remove TCE and 1,1 DCE more than 99%. The single-pass treatment efficiency for 1,4-dioxane achieved by the in situ bioreactor is 91%, and the overall treatment efficiency for 1,4-dioxane can reach 97%. For cost effectiveness, through a hypothetical remediation scenario, we found that on the 30-year total cost basis, the combined GAC and in situ bioreactor approach can cost approximately 40% less than the pump and treat approach that uses HYPOX for contaminant destruction. Regarding bioclogging, under the given site conditions and the bioaugmentation cultures used, the results show that the degree of bioclogging can be controlled with an appropriate primary substrate loading rate and an injection scheme that introduces 3 high concentration propane pulses per week, with each pulse have a duration of 6 hours. Finally, the benefit of angled wells for deep large dilute pollutant remediation was also verified through the observation of high propane concentrations in the recirculation zone and at the extraction well. In this field demonstration, we show that a groundwater recirculation system with a recirculation flow rate of 13 GPM can intercept a pollutant width of about 100 feet. At the same time, the performance of the in situ bioreactor can be established to treat 1,4-dioxane. One question we may ask is how readily we can scale this system up to tackle a treatment scenario that requires a much higher recirculation flow rate. To answer this question, we can look into 3 system components. The first component is the deep angle well for groundwater recirculation. Angle well drilling is commercially available. Drilling an angle well pair to accommodate a much higher flow rate, say 100 GPM, can be achieved using an angle well with a casing size of 5 inches or larger. Some groundwater hydraulic modeling may be needed to ensure that the aquifer permeability and the well design can support the target pumping rate. The second component is the gas substrate addition through Venturi injectors. Venturi injectors are very scalable for a wide range of flow rate. For example, a Venturi injector for a half-inch pipe can facilitate gas solubilization into water at a flow rate of a few GPM. A Venturi injector for a 3-inch pipe can handle a flow rate of 100 GPM. The length of a Venturi injector for a couple of GPM flow is approximately 6 inches. The length of a Venturi injector for 100 GPM is only 20 inches, which is about 3 times larger. The third component is the source of propane and oxygen sources. When a much larger consumption rate of propane and oxygen is needed to support the performance of aerobic metabolic biodegradation, large commercial propane tanks, for example, a 500-gallon propane tank, and an on-site propane refilling service are readily available. For a large-scale application, an oxygen generator may be used to replace the use of oxygen cylinders. Technology transfer is an important component of each ESTCP project. For our project, we have revived the 1998 aerobic metabolic in situ remediation spreadsheet tool for technology screening. This old tool was not compatible with the newer versions of Microsoft Excel program. Although this tool was published in 1998, it contained important information associated with scientific and engineering considerations for implementing aerobic metabolism at the field scale. In addition, we also published a field test design and performance evaluation Excel spreadsheet tool for in situ metabolic biodegradation. The tool is also accompanied with a user guide. This tool is aimed to help practitioners who are interested in implementing a recirculation-based field test. Finally, we also published an in-depth review paper associated with field tests regarding aerobic metabolism. Besides a review of 14 aerobic metabolic biodegradation field tests, we also summarize relevant scientific knowledge and engineering principles to make it a useful reference article for the subject of aerobic metabolism. These technology transfer products can be freely downloaded from the ESTCP webpage for the ER 185168 project. In this final slide, we summarize a few take-home key points. First, the combination of the GAC and in situ aerobic metabolic biodegradation is a competitive technology to treat a mixture of 1,4-dioxane and CVOCs. Secondly, laboratory and field pilot tests are needed to properly assess site-specific potential for this approach. Thirdly, the primary substrate used here are propane and oxygen. Because the technology will keep the aquifer aerobic, little risk of secondary water quality impacts is expected. The next point is that the most effective substrate addition approach is to keep the aerobic metabolic biodegradation bacteria hungry yet eager. Intermittent fasting is good to maintain system performance. Finally, under the conditions that the deep large dilute pollution is in a permeable aquifer that allows for a large-scale groundwater recirculation, the combined GAC and ACB approach has a clear cost advantage over the pump and tree plus advanced oxidation process approach.